So quickly do 3A, squeeze it together.
Button there on the back.
This has to connect for the safety guard to go on. Okay, part A, were you able to graph log base 2 of x? So here's our first thing, we're gonna have an asymptote at x equals 0. We are going to have a point at 1 comma 0. This doesn't change no matter which log graph you're doing, but it's a base of 2, so we have the point 2 comma 1. There's our basic shape of our graph. And now we're going to graph log base 2 of 2x minus 1. We're going to do it on a separate grid, but I'm going to write it out here. I can write it in green because I'm going to graph this one in green. Log base 2 of 2x minus 1. This is a review of chapter 3. We're going to do our transformations. The hard part about exponential graphs and log graphs is they have extra numbers in them that are part of the parent function. So the first thing I'm going to do that I sometimes find helpful, I'm going to take out a highlighter. And I recognize that I have a base 2 there. So I'm going to highlight my parent function. My parent function was log base 2 of x. This is, right, I drew that first log base 2 of x. That's my parent graph. That's my starting graph. Now, what other numbers are left? When I look at this, I see that there is a 2 left and a minus 1 left. What are these things? This 2, is it inside the function with the x? Yes. It's going to be a horizontal compression. You're going to multiply x by 1/2. What's this 1 going to do? That's going to be a vertical translation. You're going to move 1 down. So we're going to take our original points, which were 1 comma 0 and 2 comma 1. And we're going to take our original asymptote, which was x equals 0. We do all of our stretches and compressions first, and then our translations second. So what do we have to do? We have to multiply our x values by 1/2, and then we're going to have to go 1 down. So what happens when I multiply by 1/2? Well, this will be 1/2, and this will be 1, still comma 0, still comma 1. And when I move 1 down, this will be negative 1/2. Oops, sorry. 1 down will affect the y, so this will be negative 1 for your y and 1 comma 0. So I'm going to take my new graph. I also have to figure out what's going to happen to my asymptote. If you have a vertical asymptote, multiplying, because it's at 0, multiplying will make no difference because it'll stay at 0. Will moving it up and down change it? No. Only thing that will change a vertical asymptote is if moving left and right. Are we moving left and right? No. This is going to stay at x equals 0. So now we can go and graph this. We know we have an asymptote at x equals 0. We know we have the point 1 comma 0, and now we have the point 1/2 comma 1. And this is our final graph. So we did all those transformations. It's actually interesting in this graph, it's actually identical to the original graph. Even though we moved it a whole bunch, it ends up being perfectly identical. I can actually use my log laws to prove that it is exactly identical. Because this graph, this green one that we just did, was log base 2 of 2x minus 1. Yes, question?
I think you forgot the negative on.
On the one, yes, I did, thank you. Or I maybe drew it and it just disappeared like this.
No, yeah, that's, yeah.
Could have happened too, but it looks like I
I would
forgot.
not be surprised personally.
But the graph looks identical to the one that we had to begin with, and I can show you with log laws why it is. Do you notice inside here you have 2 times x? Do we have a log law for multiplying inside a log? Yes. I can change it to adding. So I could change this because there's a multiplication right here. If I wanted to, I could change this to log 2 of 2 plus log 2 of x minus 1. What is log 2 of 2? Log solve for exponents. If I put a little question mark here, what's that exponent? 1. Okay, so this is equal to 1 plus log 2 of x minus 1. Can you see that you can put the like terms together? And 1 minus 1 is nothing, so you're just left with, if you had done that, you would be like, oh, it's the exact same graph that I started with. I don't have to do any transformations. Okay, normally it won't work out to be exactly the same graph that you started with, or that nicely, but we need to know how to do the transformations. It's kind of interesting in this one, and it ends up being exactly the same graph as before. Okay, we're gonna do some more questions because we're gonna practice some more graphing, but I'll get you to circle 8, 9, 10, and 11. 8, 9, 10, and 11 right away. And then I'm going to get you to turn to page 400 because you have lots of space on page 400. So total blank page there. And we're going to add 2 more graphing ones for practice. I'm going to temporarily move this blue out of the way. And maybe I'll replace it with highlighting. So we want to graph for log base 3 of x plus 1. Yeah, I think I'll replace it with highlighting because I highlighted last time. So if you're asked to do this on an exam, the first thing you have to recognize is what's my parent graph? And my parent graph is going to be a log graph with a base of 3. And I'm going to highlight my parent graph in here. Log base 3 of x. That's my parent graph. Which means the other numbers that aren't highlighted are all going to be transformations. What does the 4 do? Outside the function, vertical. What does the 1 do? Inside the function, horizontal. What does the 5 do? Outside the function, vertical. A 4 outside multiplying, that's going to be a vertical stretch. You're going to multiply y by 4. The 1 inside, horizontal translation. Our x's are always liars. You're going to go 1 to the left instead of 1 to the right. And the minus 5 is outside, so that's vertical, and it's going to be 5 down. Now, in order to do y by 4, 1 to the left, and 5 down, you need to know what your parent graph looks like. So as a starting point, I quickly draw a graph of y equals log base 3 of x, labeling those 2 key points and my asymptote. You're going to take those key points and your asymptote, and we're going to hide this. I'm going to get you to do this first. Do your vertical stretches and horizontal stretches and compressions first, and translation second. I want you to do the mental math and see if you get the same points that I got. I have about 1.5 pages left on everybody's test, for those of you that are really wondering where I'm at with marking them. I'm almost done. So far, things are looking very nice.
Yeah, exactly. It's gonna be all good until you get to that last question.
That last question is gonna be
Yeah.
a problem solving. What's a problem solving question?
Yesterday, I was just going to wait for anything.
Have you got your 2 points and your asymptote already? How many people are done? Couple? How many people are still working on this? Okay, I'll give you a little bit longer.
Do you get that question? That's those two.
Yeah, I need that right now.
I think I got an extra negative too. Like I don't have a question.
I mean, I got there. I got
There's like a box
there
one.
was a two
It's all perfect. Cause the answer was -6, -6.
Okay, let's see how you did.
That's why I started laughing myself.
Did you get 2 -1, 0 -5, and your asymptote is, because you're going 1 to the left, is going to change to x equals -1. Now, all you have to do, draw a new grid, draw a new asymptote, draw your new points, and you have your new graph. See what we're accidentally doing? We're accidentally restudying chapter 3 you're gonna be ready for that for your exam.
I actually really like that one. That was fun.
You like chapter 3?
Yeah, that was fun.
Good one. Good one to start with.
I was so happy when
Good luck in your film. Okay, everybody good? Question.
Can I go to walking please?
Yep. For the next one, I want you to graph. So again, I'm gonna look at this. What is my parent graph? What's the parent graph?
The natural.
The natural log of x. So if I take out my highlighter, right, there's my natural log, there's my x. Everything else is going to be a transformation. What's the 2 going to do? The first one. Vertical or horizontal? Vertical stretch or compression? By how much? Right, we're gonna multiply our y values by 2. Next we get the half. What's that going to do?
Factor it out.
Oh, someone recognized. We have a horizontal stretch and a horizontal translation. So step 1, we do have to write this out in factored form. Now, sometimes factoring out a fraction is tricky. If you have to factor a half out, factoring the half out of the x is easy because it just takes out the half. But how to factor out a half out of 2? And you might get stuck. Sometimes I actually work backwards. I say, I know that I'm going to have a half here. And I have to say, a half times something has to equal 2. Then it's easier for me to see that this is going to be a 4. Does that make sense as another strategy? Instead of like thinking, how do I take a half out of 2 and getting stuck? Work backwards. You know whatever number is going to be there. If you check it, a half times what is going to be 2, and then it's easier to see that that number is going to be 4. That's a nice strategy if you're dealing with an awkward number like a fraction. So then our half is going to be horizontal. X's are liars here. X's are going to be multiplied by 2. The 4 is gonna move 4 to the left, and the 3 is going to move 3 down. So we draw our parent graph quickly. Because the base is E, you have E comma 1. Slide this over, this is our start. Those are the 3 things you're starting with. Tell me what points you end up with. I'll show you in a second. All right, are we done? Do a quick check. Did you get 2e minus 4? Comma -1, -2, comma -3. And your asymptote changes to -4. So now when you go to graph this, let's start with my asymptote. I definitely labeled -2, -3 first because that seems easy. And then in graphing 2e minus 4, the number e is 2.718281828, and then it goes on forever. So you could use 2.7 as kind of an estimate. 2.7 times 2 would be about 5.4. 5.4 minus 4 would be about 1.4. So when I went to graph it, I estimated where 2e minus 4 is. And then I draw the shape of the logarithmic graph to get the final answer.